Okay, so it's 10:15. We'll start to get started. So thanks everyone for coming to attend this Saturday Physics for Everyone. Quickly before we announce this week's speaker, in 2 weeks we'll have Professor Kevin Pitts from the physics department speaking about radiation and whether you consider it as a friend or a foe. So basically its use in the medical field. And this week, we're happy to have Professor Donna Cox with us. She's a professor of new media in the School of Art and Design. She's the first endowed Michael Aiken Chair in the university. She's the director of the Advanced Visualization Laboratory in the National Center for Supercomputing Applications, so the NCSA, just down the street. And she's also the director of the new eDream Institute. She was selected by the Chicago Museum of Science and Industry as one of the 40 modern Leonardo da Vincis for her work in sort of bringing together the arts and sciences for data visualization. And so she'll tell us today about her work over the past 30 years here at the University of Illinois on data visualization in the arts and sciences, and also her work on things like IMAX films, feature films, a lot of different ways in sort of communicating scientific data to the broader public.
Hello. I am going to thrust you in the dark. And so because I'm going to be showing a lot of different images, I just don't want anybody to get trapped with their donut on the stairs. And I have a lot of things, and it would be great if that door had just a stopper in it. So and maybe, yeah, just put something in it so people wouldn't. Thank you. So I have been here. I want to first just take you on a personal journey of why an artist is giving the colloquium on physics. So I'll give you a little history. In 1983-85, I was at the University of Wisconsin in Madison as one of the first computer artists. Now, we're talking about in the day when you couldn't get it, there was no Photoshop. You couldn't get an image on the screen unless you programmed it. So this is me, and I had built these installations. I wrote all my own software, and I used algorithms and statistics to develop the artwork. And then I photographed. This was before scanners. It was a very expensive process. I worked right next to scientists in the remote sensing lab at the University of Wisconsin. And I developed this software that would map color and image process scientific images as well as artistic images. So as an artist and a sort of a second wave computer artist, I got access to those kinds of high-end equipment, and I was also getting a Master of Fine Arts. And in those days, if you had a photograph, it cost, just to scan that photograph, it would cost me $10 to scan the photograph. And then I would take it into the computer, and I would use this software that I'd written to map into it. But that became valuable when I came to the University of Illinois in '85 as an assistant professor in the School of Art and Design as a computer artist. Now, I can tell you that in 1985, it was suspicious enough to be an artist working with a computer. But to go over and hang out with scientists was really odd. So in 1985, the National Center for Supercomputing Applications was established by the National Science Foundation. It's still here. It's up on Clark Street. And the founding director was Larry Smarr, who was an astronomer, associate professor in astronomy. And this is the Cray 1 in 1985. And this was the first time a supercomputer had come into a university environment. Before that year, non-university, usually Department of Energy, had a lot of computers. And there had been a lot of computing around after World War II to be able to predict and compute the physics, nuclear reactions, and astronomy in particular had needs of these computational ways of studying the universe. So a lot of the code was ported into the Cray that had come from other Department of Energy high-performance computing sites. But this was the first time that a computer, like at this scale, during that era in the 80s, did academics get to go to a university and use it. And we still provide that service today, and I will show you a little bit more of what that's about. NCSA is famous for not only supercomputing. It was at NCSA that Mosaic, the first visual browser, was invented. And it was at NCSA that Telnet was invented. So we have a great claim to fame over there as a result of these technologies. But the first thing was that an artist, I came with tools, software, and I came with the belief that interdisciplinary research would be the most valuable thing to this new supercomputing center as a designer of information to go work with scientists, physicists, astrophysicists. So I came here and I was at the opening. Larry Smarr invited me to present some of my computer work. Then, back in the day where you presented, remember the slide projector? Anybody remember the slide projector? You loaded your carousel and the images came out over here. So that is the first, that's an opening of NCSA in '85. And here's a few years later, this is an image of me on the Cray, done by an art photographer in 1988. Now, my first years at NCSA was, in fact, collaborative. And I had written a paper that was published in Leonardo about the future would be interdisciplinary teams that involved scientists, artists, and technologists to solve big challenges. So when I first came here, Professor George Francis, who's emeritus right now, had gone to my presentation, and we started to collaborate with the student, Ray Adasic, and we started creating, with mathematics, a sculpture machine that used and employed computer graphics in 3 dimensions to create topological surfaces. And we call this form because of its shape, the Venus series, and I used it as a sculpture machine, and it was published on many, many covers of computer magazines and simulation magazines. But this was our first Renaissance team, and the reason I called it Renaissance is because in the Renaissance period of the Great Enlightenment, there were interdisciplinary teams of artists and scientists that came together that created whole new fields of anatomy and botany because of the early collaborations. So I had the belief that Renaissance teams would help solve the problems of today by bringing visually trained, visually illiterate people together with scientists who knew the mathematics and the physics. Another Renaissance team was formed with Dr. Michael Norman, who was a professor in astronomy here, an astrophysicist, who was in that day and age most famous for astrophysical jets that he had predicted by using a supercomputer and had computed the algorithms, set up the algorithms, the physics algorithms, but he didn't have a color editor. So in 1985, I came in, it was like the hand to fit the glove. I came in with software tools to create and map color into the scalar values of the numbers that were coming out of supercomputers and to basically help bring out the morphology of the two-dimensional data. This is me. This particular astrophysical jet was shown at the big SIGGRAPH conference back in 1986, and it was the first time that that conference had shown this kind of astrophysics as part of their electronic theater. Another Renaissance team was working with a Kodak research scientist, Richard Elson, an engineer, and he and I collaborated together to take the data that was coming out of supercomputer simulations of generating plastics. And in that day, they were studying the plastic that would flow into those slide carousels that now have become archaic. But it was a tricky problem, and we took the data and designed a glyph form, that is, these glyphs to show the temperature, the pressure, the flow, and 3 dimensions in this 3-dimensional field of data that was coming out of the supercomputer. This was published on we co-published a paper on the cover of Simulation in 1988. But I was very involved in the cultural impact that this kind of data visualization would have on society. And in fact, I saw these tools that we were inventing at the time called glyphs and ways of taking numerical data and using computer graphics to represent that data. That's called data visualization, and that was what evolved. But it was having much more of an impact at that time on how we could analyze and understand, and it was a whole visual language that was being developed to communicate science, to discover the numbers, what they showed. And it was very much like hieroglyphs. That's why we call these first representations of data glyphs, because they were hieroglyphic and empowering people to read the data. So a more recent project I want to talk about is how you can take data like what is being shown here, just in this graph, this bar graph, and how that same data can be mapped into a different visual metaphor. Same data that's happening right here, over here. But through the use of computer graphics, you can actually take numerical data and show it and map it differently. Now, this was a project where back in 2002, people could wear an RFID device, and we were tracking their presence in the Baltimore Conference Center at the supercomputing conference. And they could register, and they would give us information on the interests and the kinds of categories of these sessions. These are 5 technical sessions. And this big bottom line here, that's the exhibition floor. So we were tracking their flow into these spaces. And what we did was we interactively took that data and showed it on show floors, but we remapped the data into a flower so that the same categories are represented by the petals of the flower. Here's text session 4, 3, 2, 1. The people were always worried about, well, you're going to track me to the bathroom, you're going to track me to the hotel. So the visual metaphor was actually used to help make this a playful game at the time. A lot of people said, I'd never register for this if I didn't know you, Donna. I said, I promise your data is safe. It's IEEE Viz. It was all very great. But my point here is that you can take the same numerical data and map it into different configurations using computer graphics. And those visual metaphors I call visiphores. I am going to show you more of how we map hurricanes and tornadoes in just a minute. But to go back to that era, this idea of Renaissance teams was an important concept that I brought into the classroom. And I think it's even more important today with our chancellors and in the last probably 10 years, there's been a real awareness that the humanities and the arts should be part of the dialogue with scientists in looking at the social implications of science. And in that time, I would organize classes around a project in which they would use data to visualize something, but they would contextualize it in a story that was playful, an animation. And we got international awards at that time, and it was put up in EduCom Review. And also at that time was about around the early 90s, Roger Ebert. How many know Roger Ebert? Okay. How many go to Ebert Fest? Okay, so this was just getting started. And there I am again, and here he is. He had called me into one of those wonderful Ebert Fest panels, and we talked about data and visualization and the empowerment of telling a story around that. So a lot of before he passed away, he actually reviewed some of the movies that I'm getting ready to show you that we made. But he influenced me on the power of the story around the science, not just the data visualization, but the power of the story to tell what that visualization implies for society. So back in that era, about early 90s, I started dealing with the cinematic presentation of scientific data. And what I'm talking about there is nonfiction that is supported by accurate scientific data that helps to support the story about science. And in earlier productions, these kinds of artistic renderings is what has been used. And what was different is that we were taking vetted, peer-reviewed scientific data, collaborating with teams of scientists to make sure that we're representing the data accurately, and contextualizing these data-driven visualizations by an entire story wrapped around to give context to what we were talking about with the data. The first of our work was Cosmic Voyage, and it was an IMAX film. They had heard about our data visualization. One of our industrial partners was Motorola. They funded the IMAX film in that day at $5 million when they had the money. And we ended up getting nominated for an Academy Award. And it set a precedent in IMAX films that actual data coming out of a supercomputer could be rendered with computer graphics in a production quality that could be integrated into an IMAX movie that still is being circulated around the world. And it was nominated in the documentary film section for science education, but now they don't have that category, does not allow this kind of film in. Now it goes to the Giant Screen Cinema Awards, and we're going there next week because it's being held in Chicago. In the process of making Cosmic Voyage, our first IMAX film, we developed virtual reality tools. Now, sometimes I talk to students, and they think virtual reality is new, but no, virtual reality was really the large-scale, room-sized virtual reality was built at the University of Illinois. It was truly pioneered at the UIC campus in Chicago, but the Supercomputing Center, NCSA, cloned the physical structure of that technology, and then people like myself and Bob Patterson and students, Marcus Tiebo, we built the software that would go inside the cave. How many people have ever gone to the cave when it was on campus? Okay. So the cave, this software we call Virtual Director, because we could basically put the data inside the cave and record a camera path through it, and got a patent for the ability to gesture a path in the data and fit a mathematical surface to that path. And then back in the early 90s, we also were creating avatars and collaborating between two different locations over data that was coming out of the supercomputer. And here, these avatars are in a total different location. The only thing that's being shared is the data that they see, and we each have our individual points of view, but we see the other viewer as an avatar in that shared virtual space. And that was being done in 1994 here at this campus. Well, we've come a long way since then. So to bring you up to present day, how many people have gone to the Blue Waters tour of the National Center for Supercomputing Applications? Well, here's the building being built, put together. It's one of the biggest computers. The building itself is the computer with the watering system and the cable trays and the cooling apparatus and all of the processors that have been put in there. And this is some of the visualizations that have come out of there. Now I'm going to take you just on a little trip through the anatomy of a tornado. And then I'm going to take you on this just so you can understand more clearly what I'm talking about, the visual metaphor and mapping the numbers to the visual. So what you're seeing here is we started out with a cube of numbers. And at each location in this cube of numbers, there are a whole array of numbers that represent things like temperature, pressure, velocity, vertical velocity, and all the physics that goes into this cube of data. But to really understand the dynamics, it really does take a time-evolving look at what those scalar values or the physics of this situation. So we took the stream tubes and created those to show the geometry around a tornado. The spheres, we located by analysis, locating the spheres to show the vortex of the tornado. The ground plane is showing temperature direction with cones and the direction with cones and temperature with color. So the bluer the color, the colder, and the warmer color on the periphery. And we worked for a year with the scientists on this to create and understand all the data dynamics and to put it in the form of this movie, which I'm going to play.
This supercell thunderstorm simulation was seeded with pre-storm conditions that produced an actual F4 tornado in Manchester, South Dakota. As we look inside the storm, stream tubes colored by vertical velocity represent the motion of particles released into the airflow. Spheres in the low-pressure vortex represent the developing tornado. Sinking blue stream tubes within a cool downdraft fuel the intensity of the tornado. Warm, moist air feeds the storm from the east and rise sharply upward from the surface. Tilting cones colored by temperature represent the wind speed and direction at the surface, and show the interaction of warm and cold air. A counter-rotating satellite tornado also evolves, a phenomena rarely observed in nature. This visualization represents 1 hour of storm evolution. Atmospheric scientists are evolving the complexity of their simulations in an effort to better understand and predict severe weather.
So that is data that comes in a three-dimensional numerical numbers, 1 hour of time to project and develop the behavior and study that tornado. 1 year of on and off computation of the simulation, which was done by the scientists in the Department of Atmospheric Science here on campus, and a year to actually take the data, analyze it, and develop the movie that you saw, which has really been shown all over the world. So I'm going to give you an example then. Now that's just one visualization, and you could sort of hear the story there in that describing, well, this is an hour of time. We discovered this secondary counter-rotating tornado from all the numbers. And it has been used in super tornadoes and various hunt for super twister. So it's been used in various shows as evidence that you can use data visualization. But then we started becoming more familiar with the scripts and working with these educators and producers, and we said, let us get more involved so that the computational science can help drive the story. Not just be brought in as an aftermath, but that the science itself that's being discovered can have an impact on the script. So I'm going to give you 3 film nonfiction narratives, Hubble 3D, Dynamic Earth, and solar superstorms, and give you an example of how that worked. So Hubble 3D is an IMAX film. How many people have seen Hubble 3D? Okay, great. It is primarily about astronauts going up into space and repairing the Hubble Space Station. And the director, Toni Myers, came to us. She had directed Blue Planet. And she said, we need these rendered scenes from the Hubble data to provide people with the reason why go repair a broken telescope up in, space. That was very costly. Why do it? So part of why the reason is to show people what's out there and to give them that experience. So we worked, she flew into right here, Champaign-Urbana, 3 or 4 different times, and we used Virtual Director and directed camera paths through the data, and we got the data from the Space Telescope Science Institute from NASA, and we, for the first time, showed the public a Hubble 3D image in 3 spatial dimensions of the Orion Nebula, as well as in 3D stereo. So if you want to come over to NCSA, we give tours. You can put on the stereo glasses and see excerpts, about 10 minutes of excerpts from Hubble 3D, and you'll see it in stereo. But for now, you're going to see it in mono, and well, I'm just going to show you a clip that's part of an entire scene, and this one is the visit to Orion Nebula. Now, in the history of humanity, the Orion Nebula has been studied more than any other nebula. Even the TV show Ancient Aliens say they're coming from the Orion Nebula. I mean, the Mayans, the Egyptians, there is so much mythology and storytelling around Orion, but this is the first time that people actually see the context of where it is in the night sky and what it takes to get there and how protoplanetary disks are forming there with new planetary systems. So I'm just going to show a clip, and because of copyright issues, we're not going to record any of this, right? Okay. And so, all right, the second we're going to show you is Dynamic Earth. Now, this is all about the dynamical processes, all of the physics around the globe that create such an interconnected, complicated system and feedback systems. And so we decided to co-produce one. It was wonderful working on the IMAX film, and Leonardo DiCaprio had his influence on the script, but we were just creating the visuals as part of a great big collaboration. Here, by being co-producers here at Illinois, we were able to work with scientists at the National Atmospheric Center for Research. We were able to cut a deal with Liam Neeson, and he was very magnanimous, and that's why I can show that here today, but we can't have it distributed, so we'll turn off the audio on this excerpt. Now, what I'm showing you are just data-driven excerpts from these bigger stories that are very much contextualized by live action, by other simulations that were done by NASA telescopic images to give a whole picture of the very complicated dynamics either on Earth or going up in space. This Dynamic Earth digital dome show is still very popular. It's been translated in 13 languages. It's traveled to science centers, museums, and universities all over the world. But let me just show you what we started with. Now, many of you, most of you, if you watched the news over the last few weeks, would be familiar with this kind of course, Irma hit Florida, but this kind of simulation, forecast simulation that predicts the behavior of a hurricane. Now, for Irma, they ran many models, and those were tracked on the weather station, and these are all numerical models that are supercomputing models, and they have very complex initial conditions, and there's a lot of factors that go into why Irma behaved the way it did. Well, back when we were working on Dynamic Earth, we worked with NCAR scientist Dr. Wei Wang, and when we got her data, this is all we got, and this was to simulate Hurricane Katrina. It was the biggest simulation at that time of Hurricane Katrina. And it had been available to FEMA, but there was not, computational science was trusted less in those days. I hope it gets the projections and how we think about it. It serves a great purpose in trying to predict the behavior of these complex natural phenomena. So that's the form we get the data in. Even though it's 3D, the only visualizations we had were just little slices on the land, but the data is actually 3 dimensions. So we take that data and we immediately start to try to render it with computer graphics tools. Here is New Orleans. That's that ball. We just wanted to, this is a test image of how we take the data. This has got height. There are clouds here. So it's not a flat 2D image. And this is the behavior of this numerical model of Katrina, which most closely mapped the behavior of Katrina in reality. Now, these simulations or numerical models are often set up in boxes with bounding conditions, and then they run the physics inside the box, and there's these steps that's happening. Often we get the data, it's not contiguous, or it's not continuous, or it has artifacts, but we work with this and the scientists to try to interpolate and smooth things out, because what we want to do is, for the context of Dynamic Earth, we wanted to take people inside of Katrina and give them the dynamics. So using Virtual Director, we took a sample down of that data set, and we're creating a camera path interactively. And this is our new passive stereo system that's a substitute for the cave. And Bob Patterson is interactively flying a camera through that data. And now I'm going to show you, after we get the camera path, we've got the rendering techniques, we've worked with the scientists, we've run lots of tests, and then we put it all together in the context of a much larger story about the dynamics of the Earth. And so now you can't record his voice, but you can record the visual on this. So here's Liam Neeson narrating an excerpt from the digital dome film, Dynamic Earth. I'll show you a picture of them later that was responsible for creating this. And Dynamic Earth is still being shown. It's in fact going to be the opening show for the new Dome Theater in Miami. I don't know what the status of the Dome Theater in Miami is at this time, if it was hit by a hurricane or not, but it will be the opening show, so there's still interest. Now I'm going to tell you, we're going to close with this example of a widely circulated co-production with Tom Lucas and Spitz Distributor on solar superstorms. It was a digital museum show. It's narrated by Benedict Cumberbatch, and it's been translated into 8 languages. I'm going to show you the trailer for this because I want you to get a context of some of the other work that went into the piece besides the scientific visualization excerpts that I'm going to show you next. So solar superstorms is about the big coronal mass ejections, what causes them on the sun, how they affect our power grids and satellite communications, and why we're ready for one of the biggest storms ever that's going to hit the planet. And so I'm going to play you this trailer now, and you can record this.
A fury is building on the surface of the sun. Jets of superhot gas. Rising waves of fire. The most violent explosions in our solar system. Journey into our star. To explore its inner workings. And experience the power of solar superstorms.
So as a part of the National Science Foundation project to raise public awareness about computational science, we were funded to do the data-driven visualizations part of this, but we collaborated externally with distributors and writers and producers and educators and evaluators that tested audiences to better communicate both verbally and visually the computational science that was being generated. We worked in huge computations from Blue Waters, from NASA. We processed the Solar Dynamic Observatory data. I believe that Jeff Carpenter worked directly on this. We had Blue Water simulations of the solar wind and magnetosphere. We're talking about huge grid cells that were basically cubes of data that we put into context here by putting an Earth in and tracing out the magnetic waves and really showing this, what's happening on the sun, bombarding the Earth, and used computational data for that. We also did work with to show this, as we did 8 of these, basically. We worked in 8 computational renderings. And the purpose, the goal was to raise awareness about solar superstorms and how they could have an effect. And there was a bill in Congress waiting to be funded about the funding for this kind of research. So the National Science Foundation, after the movie was made, they invited me on the Hill in the Senate building to present this whole movie as part to the aides and the senators that would come, and the House was filled. and it was hosted by Cray Research, and I showed the movie and talked about how we made it, and we had scientists there talking about the importance of being able to predict solar superstorms just like you predict hurricanes or you predict tornadoes, because we are up to have a 100-year event that could bring down the power grid and half the planet, or depending upon how it hits, or all cell communication. So that was one of the few bills in 2016 that actually passed. I'm telling you, we're very proud of that. So I'm going to show you this excerpt, and in the interest of time, I'll only show one more excerpt, and then I'll close, okay? So this is Homa Karamabadi's work, and we visualized it, and here we go. So in the interest of time, I have probably 5 more minutes of material, then I can take questions. Do you want me to play the material, or I can start questions now? Okay, all right. That seemed like a consensus. All right, here is another excerpt from solar superstorms to really explain where do these coronal mass ejections come from the surface of the Earth. These are simulations by Dr. Robert Stein, who's worked with NASA and NCSA, and it really comes from the plasma in the bowels of the star, our sun, that's reaching up and builds until it goes out of the surface of the sun. And to understand this phenomenon will help us to better predict when it happens. So here's Magnetoconvection Emerging Flux by Dr. Robert Stein and our team, AVL. So we also did a beautiful planet. I hope you get to see it. It is very much, most of the film are these International Space Station views over Earth. And we did the opening shot and the ending shot. It was shown at the IMAX in Savoy for a period of time, and it is traveling, and it's being translated into languages. But it is truly a beautiful planet, and it's a beautiful film, and that was narrated by Jennifer Lawrence. And then we just finished a 50-minute documentary that was released this summer called Seeing the Beginning of Time. You can pay $10 for it on Amazon Prime, but I'm going to cut a deal with Inga. We're going to make sure that you all get to see it here, I think. The whole show is providing context for the Dark Energy Survey and how it's a prototype telescope and data analysis of the Large Synoptic Survey Telescope. And it really interviews the heads of the Dark Energy Survey. We have interviews with the Deputy Director, Beth Wellman. It has computational science in it. It really explains how computational science and observational science go back and forth in terms of the more we see, the more it confirms the physics. We refine the physics of the numerical models, and then we get better predictions. And we basically are reverse engineering the universe through these, and through this survey telescope, and trying to understand the distribution of astronomical objects in the universe. I don't have time to play this particular one. It does show the Milky Way. I just want to point out that it is narrated by Kalina Borkowitz, and and the whole Seeing the Beginning of Time is narrated by a female. And what we've learned is that it's really important that women who have authority and knowledge also narrate these films, and we're very cognizant of to make sure that people of diverse backgrounds participate in this science and data visualization. And finally, I just want to say that I didn't cover enough of the art, but we do performances here at the Krannert Center for the Performing Arts. In 2012, we did a big performance on the Tao of Bach, and we projected images all over the theaters and had software we developed to grab the motion with computational fluid flow around human beings and project it in real time on the stage. So some of the work that's being done in science is repurposed for performance, and the performers, through many discussions, it's very synergistic with the scientists, and these are things to look out for. The Krannert is holding their anniversary in another couple of years, and we're going to be doing another big performance. So in closing, I want to give credit to my team. It takes a lot of people to work on these productions. It takes a lot of people to work on the visualizations. And for the data-driven visualizations, I'm very proud of my team, Jeff Carpenter, myself, Bob Patterson, Kalina Borkowitz, Stuart Levy, and AJ Christensen, and we work together as a Renaissance team to pull this off, and we are still using virtual reality to make our images, and I thank you very much for your time today. So we have time for a few questions,
Absolutely.
right?
So thanks again for the wonderful, enlightening presentation, and I'll turn some lights on. And we'll have time for
Turn this one on.
just back here.
Hi.
One of the largest databases we have is text.
Yes. Yes, but it's very much a different style of visualization. Now, everything that I've shown you in scientific visualization has a spatial relationship. and cubes of data. But text is a non-relation, it's a relational database, but it's not always mapped to a physical spatial environment. So the field that's grown up around visualization of like text and other types of data that like medical data is called information visualization. And our team is not specialized in that area, but you can look online for information visualization, and they have a lot of examples of the kinds of visualizations. Even a word cloud is a kind of sampling text data and making the size of the word in the cloud relative to how many times that word appears in the text. So how many of you have seen word clouds, right? Where you see, they go through and just sample all the words, and basically if the word appears 100 times, then it gets a bigger scale of the presence of the word than if it only appeared 10 times. So that is an information visualization, but it looks very different than what I'm showing with science visualization. The field is ready to just take off, and with information visualization. I tell all my students that's the area where there's going to be the most growth in research and algorithms and how to analyze and do this. But we hosted a speaker yesterday, Wendy Chun, over at NCSA, and we have to be very careful about mining this kind of data, text, and the algorithms that are being developed by Facebook and by Google, because the mining of those behaviors and that kind of data can set up racial profiling. There are built-in biases to how that analysis is being done. So any of these algorithms that we have should be opened up. They shouldn't be black boxes. We shouldn't be judging the quality of our school teachers by some algorithm that cannot be looked at. So the first step in taking text and analyzing it are samples, but then you have to run algorithms on that to see frequency, and you infer and interpret the information from that text or behaviors or the way you crawl the net. Those are interpretations, and how those algorithms work should be opened up for scrutiny, because all of our computational science is opened up. The physics is opened up for scrutiny, but not so much with our text mining and the data analysis on social media. All of that, though, we don't know what those algorithms are doing. We don't know what the algorithms are doing that analyze the behavior of our children or analyze the behavior of teachers. So what we need to have is a kind of, and I'm making it publicly, a statement about the openness of these algorithms that analyze this data and that predict behaviors, because it's one thing to predict a hurricane. Human beings are much more complex. So that's my soapbox on that one. Yes?
My question is, with the text case, you can imagine individual words and units of analysis. In the solar superstorms, and then you see what the numbers are,
Yep.
how they're gathered, what the sensor is,
Yep.
producing the numbers.
Yep.
So like, when you go into the solar atmosphere and the how do those numbers collected?
Yes. So what I showed visualizations of are the output of the numbers from computational models. And there are teams of scientists and journals being written about space weather and the behavior of space weather. There are certain instruments that are put out there that gather data. That data goes into the setup and initial conditions of many of these numerical models that are run to study the behavior. All of that is open. National Science Foundation is very open. They're publishing these. Other scientists can look at the data. Other students can get access to the models. The field is growing because of this area of validation. It's most important to be able to validate these numerical models. And that's where most of the research is going. And as you saw with Irma, you get different behaviors depending upon what physics you incorporate, what, if you take into account the land mass, are you going to judge that it may heat the temperature of what part of the Caribbean Ocean? So we're not perfect at this, but there are certain areas that if we don't develop it, it's going to lead to disaster. So the point with science is be open. It's a process. It's not a destination. It's always subject to revision, and computational science is subject to revision. So the best thing is to open these algorithms up. The physicists do it much better than the social scientists.
Speaking of hurricanes, you mentioned on news that there's like an American model and a European model.
What's
An
this?
American model and a European model.
Oh, yeah.
And then that differs. What's the difference between these two models? You know?
Yes, we've worked with, I didn't show the Cypress Institute. We collaborate with them on various models that have been developed in Europe. And they take, of course, they're developing these models, but taking data from their instruments and from local surroundings. So they're really good at predicting phenomena in Europe. Then they try to test these models against the other teams that are here in the United States. There's a team at NOAA, there's a team at NASA, there's many teams that are working, and their scientists are very competitive too. So they want to be the best at their team being the best at these predictions. So, but part of it is it's this friendly co-opetition where they are, and then they will look historically who won the Irma race, right? Who got closest. But still, these are nature is so complex. I mean, simple physics problems are simple, but you take in an open system like the Earth, it's very, very complex. So it's a matter of getting better and better at setting them up, taking into account all the conditions, and calculating. The mathematics is changing. We're getting better at this all the time. Hundreds of years of knowledge go into these publications. So different teams have different orientations, they're using different inputs, and they're trying to test one another's data. Yeah. Another question? Let me get you. In the tornado, yeah, in the cones in the tornado. Because we just limited it to the 2D on the ground, because the temperature difference between the ground and the rest of the anvil tower, there's a much bigger difference there. We know this from storm chasers that go out and experience it. They don't have to go up very far and there's a radical. So we chose to just show that which was on the ground in that instance. But in other instances, we would have three-dimensional cones suspended on the different layers. Yes?
Do you give tours of your lab?
Yes, we do. And I'm going to set that up with Inga. Where's Inga? There. We're going to set that up, and she will announce that. And I want to come back to you.
Is there a visualization of the current extinction?
The extinction of what? You know, the best visualizations that I have seen of that is done by National Geographic. Yes? He did, and he hates stereo, or he hated stereo. He did mention the Uncanny Valley, and By the way, Chris Landreth is a former student of mine. So he defined this area where with facial features that just don't quite look good enough, and it creates this kind of eerie feeling around when you see a character that doesn't quite look real. You know it. People are good at recognizing characters. How are we doing here? One more question. Burning question. One more. Yeah, that's small scale stuff. I don't know. That's really hard. Yeah. No, we've worked with nanotechnologists, and we've worked with quantum physicists, and it's so abstract. It's some of the hardest stuff. We tried to communicate that in Cosmic Voyage. And then when we did audience testing, people just got lost. So there's a lot of work to be done there to take the visualizations and to provide context around them to explain them. Okay, now the telescope is observable data, and it's collected in a 2D image, just like a photograph, with filters. And then the scientists put the mapping the color into the filters, but it's still 2 dimensions. And most telescopic images are 2 dimensions, but they have frequency, and there's additional information around them that provide us information about their depth. We took that information developed by NASA to create in computer graphics Cartesian coordinate system the depth. That was a lot of work. Yep, that was a lot of work. And then to iterate, and we developed a whole new renderer to be able to give that fluffy cloud look. Okay, well, thank you very much.